Yeah, top one to red. Okay.
Okay, good. So hi everyone, I'm Calvin. Today I'm going to talk about developing automated methods to estimate spectrally resolved DNI for solar energy applications. Now obviously this is quite a short talk, so instead of delving into all the details, I'm going to talk about three things that are seemingly unrelated. Solar panels, elephants, and the London Underground, which will hopefully illustrate the problem, the challenges, and some of the solutions that I've been working on over the past year. So, problem. And it all boils down to the fact that in face of climate change, there needs to be an aggressive move towards renewable energy. And as we saw in previous talks, solar technology is an obvious candidate in many parts of the world. Now, the most efficient technology these days are called multi-junction solar cells in concentrator photovoltaic systems, or CPVs. These things have amazing efficiencies, up to 30% in commercially available modules, and the world record currently is at 46% done under laboratory conditions. So that's pretty amazing, right? Almost half of the incident photon get translated into clean, pure, green electricity. However, there's a caveat to this number, and it's the fact that CPVs are typically optimized and tested against a standard DNI spectrum, a direct normal irradiance spectrum, at air mass 1.5 under low aerosol optical depth. Now, what's the problem with this? Well, really, it's three things. First of all, a standard DNI spectrum is highly idealistic. It assumes a fixed zolozenic angle, and most importantly, assumes low aerosol optical depth, which is not representative of the actual climatologies in which many of these solar panels are being deployed. Now, this is a standard air mass 1.5 spectrum widely used within the photovoltaic community, and it's been shown that if we assume this fixed solar spectrum, there can be up to a 15% variation in simulated energy yield. And the reason for this is because unlike sort of traditional single junction silicon cells, these multi-junction CPVs are highly spectrally sensitive. So just to illustrate the reason why, so you can see here, I don't know how to use this. Okay, so you can see here is 3 layers of sandwich semiconductors, which is a typical commercially available triple junction solar cells. And the cells has been designed in a way that each layer is carefully engineered to absorb a very specific slice of the solar spectrum. So in order to optimize and evaluate efficiencies of these panels, we need a very good estimation of the sort of photon energy distribution and hence spectrally resolved DNI. Unfortunately, most of the existing literature has been mostly focused on broadband DNI, so not spectrally resolved for less efficient solar technology. So there's clearly something that needs to be done here. Now there's a completely unrelated thing, which is also complicating the situation. So there's me taking a photo of a plane, that's clear right here, landing at London City Airport. So you can see London, very beautiful. We are here. But that's not the main point. The main point is actually the sun, right? So you can see the sun is not a point object, right? There's like a sort of glow around the sun due to scattering in the atmosphere. And this is important because multi-junction cells are typically topped with a concentrator system. These concentrator systems has very low optical tolerances. So just some numbers here. So a typical CPV has optical acceptance angle of plus or minus 1 degrees. This is inconsistent with, for example, how WMO defines DNI, which is plus or minus 2.5 degrees. Again, this is very different from ground-based measurement sensors, like pyranometers, and even radiative transfer calculation outputs if not treated correctly. So again, there's like a sort of inconsistencies in the way we sort of report, apply, measures, and DNI measurements. So with these in mind, moving forward, there are a couple of things that are quite clear. We need to routinely estimate spectrally resolved DNI for solar energy applications. We have to do so in a way that is consistent with actual optical tolerances, and hopefully also do it in a way that is based on real climatologies and observations. Okay, so with these in mind, I'm just going to talk about some of the challenges involved in terms of estimating spectrally resolved DNI. This is the quantity we're interested in. It is the DNI as a function of lambda at various positions at the atmosphere as. And this quantity can be solved by the radiative transfer equation, like that, and now it's gone, because I'm not supposed to show equations in presentations. So instead, I'm going to address the elephant in the room. So everyone imagine yourself as an elephant, and not just ordinary elephant, a skydiving elephant. And so we're up here, 100 kilometers above the sea level. This is the DNI spectrum that we would expect, right? So let's descend through the atmosphere, if possible, to see what we would expect. So at the beginning, we can see not much is happening despite having so much radiation in the top of the atmosphere. The atmosphere is so sparse that not really any scattering and absorption happen and take place. As we approach the ozone layer, we can start to see some of the attenuation due to ozone molecules, and as well as some radio scattering due to molecules. So you can see the diffuse component growing gradually here. At 10 kilometers, we're approaching some of the highest clouds, and we can see some of the water vapor pattern developing here, 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 and there. And at the bottom 5 kilometers, this is where most of the action happens as we encounter tropospheric aerosol. And you can see aerosol strongly scatters the radiation in forward direction, greatly attenuating the DNI and leaving a very strong spectral signature in the spectral DNI. So as you can see, there are a lot of factors that can affect spectral DNI: ozone, water vapor, clouds. But one of the most important things, as you saw in the animation, is aerosols. So aerosols are, as you know, solids, suspended solids and liquid in the atmosphere, highly anisotropic scattering properties, irregular in shape, size, vertical distribution, complex chemistry, and transport. So here's some examples ranging from very fine aerosols to very coarse one. So urban type, this is Blackett at Imperial. This continental biomass burning type aerosols, maritime type aerosol, and desert type aerosol. So you can see it spans a wide range, going from very anthropogenic source one to naturally occurring aerosols. So it's suffice to say that when we sort of try to estimate spectrally resolved DNI, the most important thing is actually to properly account for aerosols in our simulation and estimation retrievals. So with that in mind, I'm going to briefly present one of the DNI estimation schemes that I've been working on over the past year. But instead of talking through all the technical detail of how the retrieval works, I'm going to use an analogy, so this is the London Underground bit, about trains. Now you may ask why trains, and the answer is very simple, because I like trains. Here I am, testing an alternative career should my PhD fail. Anyway, so this is the scenario. So imagine a person wants to travel from Imperial, South Kensington, to UCL, which is at Euston Square. I'm not sure why anyone wants to go to UCL, but hypothetically speaking, it is what it is. So you're given statistics about the Oyster card touch-ins and touch-outs in South Kensington, and you're tasked with modeling how busy the station is at Euston Square. This is kind of similar to the situation we have here, where we have a satellite which we can measure top of the atmosphere irradiance, and we are asked to simulate ground-based, spectral DNI at ground. So you can see in both situations sort of highly complex interactions, and most importantly, it's an under-constrained problem. Okay, so obviously the first thing that comes to mind is to, well, we can write a model to simulate how people flow through the, not flow through the atmosphere, underground system. Much like we have a radiative transfer model which describes the interaction between photons and the atmosphere. And to run the model, we have to tell the model, where all the trains are, right? So in other words, we have to characterize the network, and much like, so characterize the network, and we can do that by, giving in a tube map. We can take it from TFL, whatever. Similarly, we have to characterize the atmosphere. The way to do it is to do, using numerical weather prediction models, probably with satellite assimilation, and we can take that from ECMWF CAMS, so it's an atmospheric analysis. Okay, so that's kind of the sort of the setup of the question, and so just move up a little bit, one little space. Okay, so as we saw just now, aerosol is important, right? So the first sort of thing we can do is, okay, we can say we have fixed a priori climatological aerosol type, feed into the model, and run it across all the simulation. So this is kind of similar to saying that, like all the passengers in our system have sort of traveled along a fixed prescribed route for probably the shortest route or whatever. So this is kind of the baseline poor man's approach to the problem, okay? And we say, oh, actually we can do better than this, right? Because different passengers have different priorities. They, for example, people in wheelchairs, commuters, whatnot, right? So they all interact and traverse through the system differently. And this is kind of like different types of aerosol, which has varying optical properties, microphysics, and size distributions. So for example, like large, small, weakly absorbing, strongly absorbing aerosols. And the key things here is that we have developed a new way to classify these aerosols. We call it spectral aerosol classification scheme. And the way we classify aerosol is much better than what existing literature has. And then, so that's that. And then the third thing we can say is that, well, if we're trying to forecast how busy the station is, so how many passengers there are on the station, by oyster card touch-in, we realize actually there is an underestimation here. So this is statistics from TfL. So as of last year, for every 100 Oyster card touch-in, actually there are 1.9 fare evading passengers, right? So that's kind of similar to saying that for every 100 photons that comes in the direct direction, there can be up to a 20 photon contribution from the circumsolar region, like we were mentioning just now. So, so we have to account for this, and we've developed a method to do this. It's called a circumsolar factor correction. This involves a lot of lookup tables and intensive computation, but this thing can be accounted for. And obviously, this correction factor depends on the solar zenith angle, the aerosol, which part of the world we are, and so on and so forth. So 1, 2, 3, these three things. In sort of more sort of academic terms, these are the three schemes: so climatological aerosol scheme, fixed aerosol types, spectral aerosol classification scheme, and the last scheme which takes into account the circumsolar factor. So in order to test these schemes, we've deployed it in Santiago, Chile, where we have done the case study. The reason is because it has very challenging aerosol conditions, and also we have in situ broadband measurements at the ground to verify the calculations of these different schemes. So this is the result. So the three schemes again. The green one is the baseline Coremans approach, right? So you can see the simulation pertains like a 10% negative bias, and if we allow sort of spectral aerosol classification, then we start to improve the bias. But it's only when we also include the circumsolar factor that we manage to estimate this broadband DNI to better than 2%, and this is well within the instrument uncertainty of at Santiago, Chile. So, so 2% translates to about 11 watt per meter square. This is the current standard literature approach, which produced minus 33 to 48 watt per meter square. So our approach to estimate spectrally resolved DNI so outperforms, well, at least as good as existing literature, if not outperforming it. So with those in mind, just a quick conclusion. Moving forward, we need to routinely estimate spectrally resolved DNI to correctly evaluate multi-junction solar cells performances. We've developed an automated method to do so, and we've also demonstrated the importance of aerosol and the circumsolar contribution. So moving forward, we need to continue to test our scheme. So we only tested in Santiago, Chile, under various climatologies. We also want to sort of have more collaboration with the photovoltaic community to understand what they need, what sort of parameters we need in order for them to be able to evaluate the solar panel performance better. And lastly, which is one thing I really want to do, is to move to a satellite-based retrieval, enabling a global assessment of energy resources. So see, these are some of the satellites I'm trying to, or envisioning to use. And that's it. Thank you.